Okay, so in molecular mechanics, bonds are modeled as springs, and it's a very simple expression to calculate the energy of a spring, which makes molecular mechanics extremely fast, which means that we can scale it to thousands and thousands of atoms. So the calculations we did yesterday, the XTB you can do on a lot of atoms, but you can't do on 10,000 atoms. And certainly the Gaussian calculation was a B3LYP. It was a density functional, hybrid density functional calculation. You certainly couldn't do that with a system that contained thousands and thousands of atoms. For molecular mechanics, you can. And it is immensely powerful in that we can get an optimum geometry. We can also do conformational searches. You can imagine that if you're trying to find thousands and thousands of conformations, you need something that's really fast that will very quickly provide you with an energy for each of the conformations. And we can explore normal modes of other things like normal modes of vibration. Please, back on this one, there are things that molecular mechanics can't do. So if you're interested in anything on your molecule that involves orbitals, if you're looking at absorption of light for a molecule, molecular mechanics isn't really the perfect choice for that. So if you want to know anything about electrons in your molecule, we can't use molecular mechanics. But if we're talking about geometry, if we're talking about conformation, molecular mechanics can do it, because all it needs to know is the distance between the atoms or the relative geometry of the atoms, and then it will provide you an energy related to that particular geometry of your molecule. Okay, so in molecular mechanics, you have a total energy, and the total energy has many terms. Please, depending where you look, you will have different terms, but the common ones, the most ones that are common to everywhere you look, will be your bonded terms, stretches, bends, and torsions. So if you have a look at the blue here, stretches, bends, and torsions are everywhere you look. No matter who's doing molecular mechanics, you'll see these three terms. And you'll also see these two terms, no matter where you look, the van der Waals and electrostatic terms. And those all will contribute towards the total energy of a molecule. Right, now depending where you look, there'll be some other terms, and sometimes there will be cross terms, outer plane terms, etc. Yes, those are just refinements on the total energy. People refine the expression in different ways, but ultimately what people are trying to do is trying to get the total energy of a molecule dependent on every single bond in the molecule, every single angle in the molecule, every single torsional angle in the molecule, and of course, taking into account close contacts or far contacts, and taking into account the charges on the atoms and how the charges interact with each other. And that provides an expression for the total energy of a molecule. So I'm just going to go on one by one fairly quickly through this, just to give you an idea of what it looks like. So, of course, for a bond, you can imagine two atoms, and they have a bond, and they are connected to each other. And of course, sorry, this should be so. As you move it away, so if the A and B are at equilibrium, the energy will be at zero. So you see in this graph, if A and B are at equilibrium, the energy is zero. But of course, as you move away, the energy goes up, and we find a parabolic curve works quite nicely for this. So if you have your distance away from equilibrium squared, and if your distance is positive, the energy is going to go up. If the distance is negative, again, it's squared, it's also going to go up. And so if you try and move those atoms away from their equilibrium distance away from each other, you're going to see an increase in the energy in both cases. So the lowest energy you can get for a bond is when it is at its equilibrium bonding. Okay. Of course, there may be situations in your molecule where two atoms can't be at the equilibrium bonding, but that's fine because we can calculate the energy cost. And that energy cost of having them not at that bonding may be compensated by some by some easing strain elsewhere in your molecule. So uh, we treat all bonds like this, but of course, to do this, we need to know two things. We need to know what is the equilibrium bond length for the two atoms. So what is R naught? What's the equilibrium bond length for the two atoms? And we also need to know a force constant. So it's how stiff that bond is or how loose that bond is. And you can imagine that for a triple bond, it's going to be an extremely high value for K. And if you've got a single bond, a weak single bond, they're going to have extremely low value for K. So in a weak bond, it's going to be easier to move away from equilibrium. But in a triple bond, it's going to be more difficult to move the two atoms away from equilibrium. But ultimately, if you know those two values, and if you know those two values, and you know the actual distance the two atoms are apart, you can calculate the energy then of having those two atoms in that arrangement. Okay. Now that the squared nature of that, the parabolic nature of that, might not be entirely correct in terms of dealing with bonds, because you will know that if you take two bonds and you move them further and further apart, you can eventually break the bond, so the energy doesn't go up to infinity. But of course, in the expression that I've just given you here, if you make the distance from equilibrium go a bit larger and larger, if this tends towards infinity, then of course your energy is going to tend towards infinity. And so it's going to be impossible to move those atoms to an infinite distance apart. So that does deviate from reality. So if you're trying to move your atoms and break it, then of course the molecular mechanics energy just goes up and up and up to an impossible value. So is this bad? Yes, it's bad because we can't look at atoms that are too far away from equilibrium. But is it really that bad? Because normally we're interested in molecules where everything is close to equilibrium. We're interested in the lowest energy conformation of a molecule, and that doesn't have atoms far away from equilibrium. So it's not too bad. And so when you look at the curve that I had on the previous slide, with the more familiar Morse curve that you're probably familiar with, where you try and how atoms behave in relation to each other, you'll see that right close to equilibrium, there is a match. And so dealing with a bond as a spring is fine if you're not too far away from equilibrium. And certainly it's going to it's going to force in your model all of your atoms to be close to equilibrium bond lengths. Okay. Please, you don't forget that with molecular mechanics, we've got to get the total energy of a molecule, and the molecule may have many bonds. And you can see here, you've got some bonds that are far away from, see this bond here is far away from equilibrium. So we've got to calculate that energy term. That's far from equilibrium. That's actually not too far from equilibrium, etc. And you see this is being compressed. So it's far. So we're going to have to calculate 1, 2, 3, 4, 5 terms and sum up those 5 terms, and you get the total energy for a molecule by summing up those 5 terms. So that is the E stretch term. That's the first of the bonding terms that we have. Okay. We deal with angles in a similar way. So hang on, this is a stretch, sorry, not angles yet, but of course, here's an example with water. So in water, the HO bond length is 0.96 angstroms. And so you've got that K into R minus R naught squared. The K, I think this is the amber force field. The K is 553 kilocalories per mole per angstrom squared. And so if we look at some bonds, you can see like if your bond length is 1.26, it's clearly not at its best at the equilibrium bond length. It's clearly not. So we can put 1.26 in there. and the energy is 553 with 1.26 minus equilibrium, and we can get an energy value equally out there. And similarly, you can see this is compressed. It's too short compared to the equilibrium bond length of 0.96 angstroms. So we can use the expression 553 into its actual bond length minus that, and we can get an energy value for that. So we get the energy value for the two bonds. And of course, E stretch is the sum of both of those, and we get 996 kilocalories per mole. Okay. So if you've got any molecule, and it doesn't have to be as simple as water, it could have thousands of bonds. You just, with a computer, it's easy to go through each one of those 1,000 bonds and calculate an energy of each one based on their distance and what it should be for a carbon-carbon or a carbon-hydrogen or carbon-nitrogen, etc., or a carbon-carbon double bond, etc. You sum up the energy value you get, and you can see what the energy is of all the bonds in the molecule. Okay, that's the first term. But of course, we have to deal with angles in a similar manner, because you could have your bonds perfect, absolutely perfect, but then have the angles incorrectly organized. So again, for 3 atoms, for instance, we know that if you've got a tetrahedral carbon atom, maybe CH, 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 take methane, for example, CH4, and then the angle HCH, we know should be 109 degrees. In a molecule, if it's not 109 degrees, we've got to add an energy term to it that will force it, in the low energy case, to go back to 109 degrees. And so we know what theta naught is. It's 109 degrees. And if it's not 109 degrees, we can have a constant for that particular angle. So if it's an HCH angle, we'll have a constant for it, and we can calculate the energy due to it not being at the equilibrium bond angle. Okay. And of course, you can't just, in a molecule, there'll be many angles. So you can see over here, remember we had 5 bond lengths here, but we've got lots of bond angles here. We've got 6 bond angles here. We've got to calculate the total E bend from all of them. You can see in this case, see this bond angle is not right. It should be the equilibrium bond angle is shown there. And so there'll be an energy cost for each one of these 6 angles. Okay, so we've got to do that. So in our water example I had there, it's interesting that I had the angle as being 109.5. What's interesting is that the equilibrium bond angle for water is 104.5. But be very careful of units, because in software, often the terms are all according to radians. And so the equilibrium bond angle, I'm converting from 104.5 degrees to 1.823 radians. So this angle here at equilibrium should be 1.823 radians. And it's not 1.823 radians. It is, if we just do a conversion, it is at 1.911 radians, which is not quite right. You see the actual angle is 1.911. The equilibrium angle is 1.823. And so because it's not at equilibrium, we can calculate the cost of not having it at equilibrium. And so it's 100 kilocalories per mole per radian squared. And we can calculate, and we can see the energy cost of not having that at its equilibrium bond angle is 0.774 kilocalories per mole. What could we do to lower the energy? Well, we need to reduce this angle until it's exactly 1.823, and then this energy will go down to exactly 0. But as it is, we have that angle, we have energy to that angle. And of course, the E bend term, we've got to sum up all angles in the molecule. In this case, there's only one angle. So E bend for this molecule is 0.774. Okay. Of course, we had already calculated E stretch for this molecule. and we got 99.6, and we've just in the previous slide calculated E-bend, so your total energy for the molecule is you'll add those two together and you'll get the total energy. Okay. Right. A third contribution to energy in molecules is the torsion energy. And I just want you to be aware that the torsion is tricky, and we can't just use an x squared type of arrangement to calculate the torsion angle, the torsional energy, because in different situations you might need the energy to go up many times as you circle, or less times. So you can imagine, for instance, if you've got something like maybe an amide bond or something where things change when you rotate every 360 degrees, you'll see that you might have, just imagine you've got 4 atoms like this, just 4 atoms and there's nothing else. You can imagine that there will be one, if you rotate around this torsion angle here, Newman projection, if you rotate D around, at some point it will interact with A, and for the other 360 degrees it won't. There'll only be one maximum, and so the energy profile will look like this. But if you've got ethane, which has 3 bonds here on this side and 3 bonds on that side, then as you rotate around, this will interact 3 times as you go through 360 degrees, and your profile will look like this. So in ethane, your profile looks like this, because every time it comes across a bond, you get to maximum. So you get the eclipse conformation, then the staggered, then the eclipsed, then the staggered, then the eclipsed, many times around. So if you've got ethane, this is an appropriate profile. If you've got something with only 4 atoms, this might be a more appropriate profile. So you can't just have one expression that fits everything. You've got to think very carefully about your exact situation that you're working with. And a cosine function works really nicely. A cosine function is fantastic because if you have cosine of theta, you've got something that looks like that, profile that looks like that. So cosine theta may work in some cases, and cosine of 3 theta may work in other cases. And so you just have cosine as your basis, as your basic function, and then you just adjust it according to the situation that you're in. Okay, so can I show you how we can adjust the cosine function? So have a look at this. This is hydrogen peroxide. I'm looking at it. It's H. There's an O in front. There's an O behind. So it's H2O2. So H, O, and this is Newman projection. There's an O behind, and this hydrogen here is attached to the other O that's behind. Okay, and this is the equilibrium bond angle. This is currently at equilibrium bond angle, and so this should be an energy of 0. No, I think it should be more 95, but it doesn't matter. Let's say the equilibrium bond angle is 115. How can we adjust the cosine to make sure that the energy is naught at 1.5, at 115, and that the energy increases everywhere else you go? Okay, so if you start with a cosine function, the first problem you have with the cosine function is that cosine goes between +1 and -1. And you don't want negative energy. The lowest energy you can have is 0. So the first thing you do is you're going to add 1 to your cosine function. And that solves the problem of no negative energy for that. But the problem is that it goes up to 2. And the energy goes up to 2, not to an energy maximum that you'd want. So the question, the first thing is you're going to have to do is you're going to have to divide this all by 2 and then multiply it by the maximum energy you want it to go up to. So if V is your maximum energy it can be, you'll have V over 2 times that 1 by cosine theta, then scales the whole cosine to be its correct thing. The problem being now is that the equilibrium bond angle here, the lowest energy is at 180 degrees. So E is naught at 180 degrees, and it's a maximum at 360 degrees. Yes, question? Hello? Okay, so the problem is that the minimum is not where you want it to. And so what you can do is you can introduce a phase, and you can make a phase, put a phase in of where you want the maximum to be. And so that phase then will shift it so that you can see there's a minimum at 115 and the maximum is not quite at 360. So the form of the torsion angle term can end up being quite complicated. But of course, if you build it up one by one, here's another case. Here's ethane. Ethane, here's the front carbon with your 3 hydrogens there. And you can see we've got a staggered conformation. And as you rotate it around, you want to clip staggered and so on. And so here it's at 0 degrees. And so we want a high energy. And at 60 degrees, we want low. And then 120, we want high. 180, we want low, and so on. So how do we change a cosine function to match that? Well, let's start with a cosine function which goes between 1 and -1. And you can see there's only one maximum, which is a problem. So what we're going to do is do cosine 3 theta to make 3 maxima. So it will be eclipsed, eclipsed, eclipsed. So there'll be 3 cases per 360 degrees where the energy goes up. Okay, but then we've still got this negative energy problem. We just do 1 plus cos theta to push it up. But then, of course, our energy goes between 0 and 2. We need to scale it to E max or V. And so we just do VO2 times that. And so we get a nice profile for our ethane as we want it. Okay, so just please be aware that in software, all of this has to happen. And yes, you might be throwing this great big molecule with thousands of atoms at it, but of course it's going to have to go through and decide where all the angles are and decide the appropriate torsional term to use, and then apply that torsional term to each of those torsions and calculate a total energy of that. Okay. Sorry, it can be even more complicated than that. An amide is a nice one, which it doesn't really follow a cosine graph at all. You have a look at this. You see a cosine goes down to 0. It goes down to minimum, maximum, minimum, maximum. But you see with an amide, you've got something slightly different. You've got a higher minimum to a lower minimum to a higher. So you've got a local minimum. This is the same local minimum to a global minimum to a local minimum. And that's not quite a cosine graph, but fortunately, you can build up a shape like this by adding cosine functions together. So if you really want to get an accurate amide bond with the cis and trans for rotation about the NC of that amide bond, you might have to add cosine functions together. And so that might be the way to deal with it. And of course, the software is going to have to pick that up, and the software will pick it up and we'll be able to calculate, say, this is the profile that we have to use for that particular dihedral angle, for that torsional angle, and it will then provide an energy value for that particular torsion angle in that molecule. Okay. So don't forget that if you've got a general molecule, there'll be many torsion angles. So can you see this red line here? Those 4 atoms are at 0 degrees. And so we need to calculate the energy cost of having those 4 atoms in that arrangement. See the green one here? Those 4 atoms, that dihedrals, that torsion angle is at 180 degrees. So you'd have to calculate the cost of that. And of course, there's the yellow one and there is the blue one as well. So you have to add up all of those terms to get a total energy from torsions in a molecule. Okay. So those 3 cases, we've done stretches, bends, and torsions. Those 3 sets of interactions are through bonds. Those are bonding interactions. And those are one main contribution towards your total energy of molecule. Now, of course, you also have non-bonding interactions. So we've got non-bonding interactions, and those are van der Waals and electrostatic. These are for atoms that are at least 4 atoms apart. Okay. The van der Waals is really for, they offer non-bonded atoms at least 4 atoms apart. And we use, for van der Waals, we use a Lennard-Jones potential. Okay. Now, if you really want to go into van der Waals interactions, I don't want to spend too much time on this. Van der Waals components, van der Waals interactions are a mix of many components. So there will be repulsive, there will be dipole interactions, there'll be induced dipole interactions, there'll be dispersive forces. What's interesting is if you have a look at the dipole interactions and the induced dipole interactions and the energy from dispersion forces, you'll note that all 3 of those are dependent on the distance between atoms. And have a look at the distance. So the energy from the dipole, the induced dipole, and the dispersion interactions, notice that there's a really important term, r to the power of 6. So this r to the power of 6 is quite important. And if you were to then say that, hang on, these are too complicated to work with separately, let's try and work them together and get the right form of potential. You'll notice that all of these here are dependent on something of r to the power of 6. So if you want to model that van der Waals interaction, if you have 1 over to the r6 as being the attractive component of your van der Waals, it will match experiment quite well. It'll match theory quite well. So here is the form of a Lennard-Jones. This is a Lennard-Jones potential. And we use this for van der Waals. And this here, it has an attractive part. You know, if you've got 2 atoms that are just floating around, there will be some attraction to each other. And that's how we can, for instance, we can liquefy noble gases, for instance, because there's an attractive component of van der Waals. But of course, if you try and push 2 atoms too closely together, you've got a repulsive component. And so we have the attractive component as power 6 based on what it should be. But of course, the repulsive should really be exponential. But in the Lennard-Jones, it's done to the power of 12 to make it a really bad, a bad clash. And it's, I think the reason for this was that if you're calculating something to the power of 6, just calculate everything to the power of 6, and you can then square it. And that eases the calculation, makes the calculation go a bit easier and faster if you have that kind of potential. So this is what it looks like. So what we have is the to the power of r to the power of 12 repulsion, r to the power of 6 attraction. And so, of course, if your atoms are too far apart, they'll be attracted to get to a distance together. If they're too close together, they'll be repelled to get to this distance. So the van der Waals is attractive when atoms are far, repulsive when atoms are close, and we use this 612 Lennard-Jones potential to model that van der Waals interaction. Okay. Of course, with non-bonded, if they've got charges, if those non-bonded atoms have separate charges, then of course we need to know that like charges repel and unlike charges attract, which means that if they're repelling each other, we've got a positive contribution to the energy. If they're attracting, we've got a negative contribution to the energy. And so we need to include that electrostatic charge in it. Okay. And then, of course, we sum those over all pairs of non-bonded atoms within a reasonable distance. So this is electrostatic and van der Waals is over all pairs. Here's the sum of all pairs. Here's your electrostatic term, which is dependent over R. And here's your van der Waals, which is the 612, the Lennard-Jones. And so that then contributes towards the total energy. Okay. Right. And then, of course, there are other terms that I don't want to go into. There's sometimes cross terms and outer plane terms that are added, and that's just to refine your total energy of molecular mechanics. But ultimately, your total energy of a molecule is you add the stretches, the bends, the torsions, all the bonded terms, and the bonded, non-bonded terms, and whatever refinements you have to get the total energy of a molecule. If you want to do a geometry optimization, you're going to have to change bond lengths, angles, torsions, and relative positions of atoms to each other to try and get this energy to be the lowest possible value it can. But of course, the exact equation you use, including refinements and the parameters, is called a force field. And so examples of force fields are the amber, charm, and Gromos force fields. Okay. So it is really a very efficient way of cleaning molecules. It's really a fast way of cleaning molecules. But of course, there are problems with it. We may know what a carbon-carbon single bond length should be in terms of equilibrium bond distance. We may know what it should be in terms of the force and how the energy changes as you work it. But do we know about a copper-carbon interaction, etc.? So lack of parameters can be a problem. We've got 92 natural elements in the periodic table. And of course, just with a single interaction, it's 92 squared, possible differences. And of course, when you take double, triple, single bonds into account, carbon-carbon bond is different to carbon-carbon double bond. There are so many numbers you need for this. Lack of parameters can be a problem. But it's not too bad a problem because I think part of the work I do is where there are missing parameters, we actually look at accurately calculating the parameters to add to a force field to work with it. Okay, so that's how molecular mechanics works. We'll be coming back to this again and again. Please just run through it briefly after this, and in the next lecture, I'll be speaking about what we can do with this in terms of calculated conformations, etc. Okay. So can we pause for a moment, and then we'll meet in about 10 minutes for the actual practice session of this. Any comments before I close off? Okay, well, if you do have any questions, then please send them my way. Okay, so I'll meet in about 10 minutes on my other computer, and then we'll look at how we're getting in terms of getting calculations onto the cluster. Okay, so I'll see you in 10 minutes time.